Hello, John Levesque here. This video is going to cover the memory analysis that is available within Perfttools. The name of the module that we will be loading is perftools-lite-hbm. This video is going to also use a new application. Leslie 3D is a CFD code. One of the spec MPI benchmarks. So the very first thing we're going to do is load Perfttools-lite-hbm. Now you get some information out of this about using Reveal with this tool. However, that is not necessary. Basically what we're going to do is just be looking at the text output from the tool. Now, this application has a nice make file, so we'll do make. Notice that I am using this -h list equal a. This is going to be generating some LST files that gives us information about how the compiler optimized particular routines. I think we've covered this in previous videos. Alright, so we're close to finishing this build. Notice it is now instrumenting the executable with the HBM instrumentation. Okay, so we are going to be submitting this to a Broadwell system. We are going to, I should have cut down this wall time. I don't need that much. 8 nodes, 32 MPI tasks on each node, the executable, and we're going to this output file. One thing I just noticed that I want to do, I want to edit this, and very important because it turns out that this Broadwell has more than 32 cores per node. And I want to make sure that these 32 MPI tasks are evenly distributed on each socket. So that's why I put this S16 on here. Okay, so let's Q sub this. Alrighty. And do a Q stat to see if we're coming in there. And we started running. Notice that we have an output file. And we can tail this. Alright, so it's running along fairly quickly. It's going to run 500 time steps. It shouldn't really take too long, much longer. We're almost there. And then, so this is the output from the program. And right after that, Perfttools puts out the memory analysis information. So here's the end of the 500 cycles. And now, here again, this is the version number we're using. The experiment is Lite-HBM. There are 256 MPI ranks, 32 on each node. No OpenMP. The number of cores per socket is 22. So this Broadwell has 44 cores on the node, and we're only using 32 of those. Okay, and this is when the execution time starts. This is the clock rate, the family and model number. Now this is, it ran for 27 seconds. The high memory is 67 gigabytes. each MPI task used 263 megabytes. All right, and now we're going to be looking at two hardware counters. One is this memory load operations retired. Now, one of the issues with this is not only is this going to count actual data that the program accesses, but it's going to count any prefetching data that might not be used. And now down here we have the object sample wait and count. The difference here is the other hardware counter we're looking at is stalls. So if a particular memory operation is also associated with a stall, it is weighted higher. So you notice that this is these are pretty much all weighted a little higher. Okay, now this is the size in each MPI task of the array, and it's telling you where it is allocated, which is very nice to know. Now this table is sorted by the object sample weight, whereas this table is sorted by object sample count. Other than that, same information. Okay, now let's go down because this is where we get into more interesting information. Table 3. Okay, and now here are the two hardware counters that are actually gathered. All right, now what this is doing is showing us percentage-wise which routines are using most of the memory bandwidth. So these are the major computational routines, and they are actually utilizing most of the memory bandwidth. Now the other thing you see is, so this is the number of stalls. This is more an indication of where the computation is waiting for data to come up. Okay, so that's very nice. But this is what is just very nice. So this is showing us for each routine listed above the actual line numbers that are incurring most of the stalls. And so what we want to do is look at flux x or flux k.f. And let's look at line number, let's see, the one with the highest is 71. So what I'm going to do is I'm going to bring that up. That happens to be in source. And I want to look at list, which isn't in source. So flux k.lst. And here again, I'm kind of looking for line 71. Huh. That's bizarre. Sorry, I wasn't in the editor. So I'm going to look at flux k. All right, and we're going to go to line 71. All right. So this is very interesting. So this is beautiful. There are a couple things going on here. First, what this is saying is that the compiler is blocking, it is inverting, it is vectorizing, and this, like this particular loop is only 5. We have array syntax. I hate array syntax because it really does not utilize cache well. The other thing is that the compiler does not always do a good job of blocking a loop. And so very often what we like to do is pretty much completely stop the compiler from doing this blocking. Whenever we see this B in front of a multi-nested loop. This D down here, the compiler knows that IChem is not greater than 0. So it's not doing, it's deleting this. But what this is saying is this is getting a lot of stalls. So what we're going to do is rewrite this. Okay, so what we did 2 things. First off, we unrolled this. This is always 5. And so what we did is we replaced this do loop with 5 statements. And we just replaced L with 1 in the first statement, 2 in the second, 3 in the third, 4 in the fourth, 5 in the fifth. The other thing we did is we got rid of the array index, the array syntax. We put in a do loop that basically now is going, the advantage to this is all of these are going to be being updated at the same time. And so we're going to be able to get some overlap of computation. There is some reuse. Notice DTV is used in every one of the statements. So that will remain in cache. The other ones are, that's the only reuse that we're affording here. Okay, so now we're remaking this, there we go. So another HBM is being generated. Want to see if that line 71 disappears now. Bet you it does. All right. Then now we'll Q sub. Now, while that is running, let's look at the compiler listing. Okay, so now we're still getting some blocking. All right, and so one thing I might even do is put in a directive to stop the compiler from blocking these 2 loops. I just don't like the compiler doing its blocking. We'll see how the performance looks on this. All right, now let's see. So we have the output file. So let's look at that. All right, and we'll go forward to okay, flux K, line 71 disappeared. Now line 75 is still here. So let's go back and look at that. This time I am in the editor. So 75 is still in here. So what I'm going to do is I'm going to put in a directive to stop its blocking. All right, let's show you what I did here. So I put in this no blocking. Notice that we don't have B's anymore. And let's submit this. Man, that was either really fast or it hasn't started yet. Nope, it's still running. There we go. All right, so let's go back up here to flux. Well, 75 is still in there. But remember before that this area of code was hitting most of the stalls. And at least now the number of stalls has gone down. Let's look at line 66. So 66 is kind of, now this is interesting. 66 is this call. And that call is inlined. So basically what it is saying is in this routine, there are a lot of stalls. So let's look, that routine happens to be in here. Here we go. It is vectorized. No array syntax. All goodness. Pretty long routine. Long loop. And look at this. What the compiler is telling us is this loop is using more registers than it can keep track of, that it can do good register allocation on. All right, now if you look at this, there are a very large number of scalar temporaries. Now, this is kind of a bizarre twist, because usually what you try to do is use scalar temporaries to reduce memory movement. Well, in this case, it turns out that if we make a number of these arrays, just small arrays the size of I, that the register allocation issue goes away and this thing runs a little bit faster. I have done this, you know, it works pretty well, but it's probably beyond this particular video because we're already 19 minutes long. So, I hope you enjoyed it. I am going to be looking at Leslie 3D again, but this time from the aspect of parallelizing, putting in OpenMP directives. Thank you very much for your time.